And we're live from downtown Mill Bay.
I bet one of the future doctors, like in the next 3, they will have a season where the TARDIS actually blends into its surroundings.
That'd be pretty
Most of our boss will be gone for business.
cool. Okay, quick attendance. We are Block E, and there's a lot of people away. Aiden, not here. Arnie,
Yes.
Bowen,
Hello.
Graham,
No.
no Graham. Grayson, Jamie,
Yeah.
Layla,
Yeah.
Liam,
Here.
Murray, Matthew, Miyabi, no Miyabi. Nick, no. Is he?
He's a bit sick. So.
Okay. Noah,
Noah just like spontaneously combusted.
what?
I haven't seen Noah in so long.
Noah's in the business trip.
Yeah. Rachel,
Yeah.
Rose,
Noah doesn't actually spontaneous.
Violet, and Yuma. We're not too bad down for the business trip. And these are all the students who actually care about science and are going to go on and do well and eventually succeed in life. Whereas those business students will just have sad, pathetic lives worried only about money. Or the other way around. We'll see. Last day, we just started energy in bonds. If you can pull out your notes, we're going to do the first 40 minutes, and this last 40 minutes will be the second part of the lab, or the first part of the lab if you missed the first part. And then we'll head out there. We made a gummy bear scream last class
That was fun.
to show that you had to have a certain amount of energy to stop, not to stop, to start a reaction. So, if I was, nah,
Isn't like
I
a
don't like that one.
spontaneous reaction a reaction that requires no extra energy?
nope. It means the energy is already present in the environment around it. Because there is always energy. If you didn't have any energy at all, it'd be absolute zero.
You don't talk about absolute zero.
Not since the incident, anyway.
What did my notes
The
say?
incident.
Yeah, the incident.
So, the activation energy is the energy required to start the reaction. What type of reaction is this that we saw with the gummy bear? Exothermic. And that means the energy is passed to the environment. As we saw with the gummy bear. The products have, now in their bonds, if energy has come out to the environment, do the bonds that are left have more energy or less energy?
Less.
Less. This is a measure of bond energy, so now they have less. Products have less energy in their bonds. And our axi, reaction progress is at the bottom. It's not time, because it's not the time of the reaction, because the reaction may not happen. So this is assuming the reaction would happen. What is the amount of energy? That's all that means. So it's like time, but forcing it to go. And then when we say potential energy, we mean bond energy. If the amount of energy in the bonds is going up that way and coming down the other way, where I was marking it as here. Why are you so late?
I got to the sale and I realized I forgot my computer, so I had to run back and grab it.
So you went back to get more prepared. Well done. Where do in this process, we've got bonds from H2 and O2. And we're making, on this side, H2O. So we're going to break the old bonds, and we're going to make some new bonds. On this diagram, where do the bonds break and where do the bonds form? Do they break going up, or do they form going up? And do they break going down, or do they form going down? Or do they both do both at the same time? Yes?
They break when it starts going up
How come?
because it releases the energy to the environment.
it does eventually, but when does it release the energy to the environment? Because it is the energy being released when the graph goes up, or is it taking energy in?
Early energy.
It gives out the energy when as it falls,
Yeah, as it falls. So this part is the energy to the environment. And represents one of the two fundamental forces of the universe. Should I tell you? Yeah, maybe. This part here, from where you start to where you end up, is known as delta H, or the change in H. We refer to it as the change in heat, because heat is often involved. And this one, because it's coming down, it is negative. For exothermic reactions. I'll probably never ask you for delta H, because that's actually a Chem 12-ish topic. However, it's just letting you know that it's coming out. So this is where the energy came from, that came out of the gummy bear after we lit it on fire. But first we had to put energy in. And this is a graph of potential energy. So where is that? Where is energy in the potential energy? Where does that go into? It's the bonds. So if you have a higher potential energy, do you have more bonds or less bonds? More bonds, like so many bonds. The greatest bond fill ever, and when they have a time machine, and they go get all the bonds. Can you imagine a crossover between Doctor Who and a Bond film, and then we had all the bonds?
That'd be awesome.
So this way we form bonds, and this way we break bonds. So we actually don't break any bonds until it falls down the other side and they all start snapping apart. But you form them all going up. You get sort of a weird structure in the top that's made of every single bond. It has both a Scottish accent and an English one. You could do so many bond references. The equivalent for that. Let's see. Never open that shelf again. In the equation, H2 plus O2 goes to H2O. Balance it. How many H2s and O2s do I need? Two H2s. See if this works. I don't know if this will work as well as the little ones, but it'll be faster. So these have to come together just right in order to make water. Oh, and I've already broken. And instead of them all breaking apart and then putting them together like you probably would if you were making it, in chemistry what happens is it kind of makes, can I get it to stick there? It is magnetic, but it doesn't want to because that's not a perfect spot. It makes kind of a structure with literally every bond. So that's what it makes going up. It's got every single bond. It's called the activated complex. And then when it goes down, it breaks, and then you get the final product. And then you get the Mickey Mouse ears. So you form bonds going up, because that's literally bond energy. You go down, and then you have bonds coming out. So, based on that diagram, Which one of these has high energy bonds and which one has low energy bonds? Pardon? Which has high energy? Light?
Left.
Left, thank you. How many of you are sick in some way? I'm going down fast. Don't worry, the flu shot's coming. I think they've scheduled it for the end of the month. By then you'll have all had the flu. Pardon?
We did that.
Oh, did you?
I-
That's not the flu shot.
I missed.
You got a
That
pre-flu
was
shot.
the appointment thing, right?
Yeah. They're going around stabbing you.
There's more flu shots?
I think so.
I missed.
Well, either that or it's COVID, because COVID's just a flu now. Well, not just a flu, but it's another flu.
I missed my shot because I was sick and now I don't know what to do.
Oh, you go to any pharmacy and you make an appointment. So get your parents to make an appointment and they'll just give you a flu shot.
Okay.
It costs like $10. Get a flu shot. High energy bonds, low energy bonds, and so if you're giving off energy, it's called exothermic. And you have a graph that looks like this. You go from high energy to low energy, and the leftover comes out. And then if you take in energy, you are endothermic.
Skeletons.
Like, what? Skeletons?
Exo and endoskeleton.
Oh, yeah, same roots. Takes in energy, and you get a graph that looks like this. You go from low energy bonds to high energy bonds. The mitochondria.
That was the powerhouse of the cell.
We didn't have a chorus there. We had like 3 people. 1, 2, 3. The mitochondria.
Is the powerhouse of the cell.
I guess you are all a little sick. So that was pretty good.
Disappointing, man.
C6, H12, O6, plus oxygen. That's sugar. You burn it in your mitochondria, and it gives off CO2 and H2O. And what else does it give off that you were told that mitochondria did? Were you told ATP? Often they'll just say energy, and the reason this works is because this has high energy bonds. And it takes some of that energy. These have low energy bonds. So that helps drive the reaction this way. It's going to low energy, but this, very high energy bonds.
What is ATP?
It is adenosine, which the structure of which, who cares? Attached to a phosphate group, attached to another phosphate group, attached to another phosphate group.
Oh.
So this is adenosine triphosphate. You've got 3 phosphate groups. Those are high energy bonds. Because it's easy to say mitochondria is a powerhouse of the cell. But like, you're not a combustion engine. They don't take glucose and like burn it and it like explodes a piston and drives an engine. Like, how do you get the energy to the enzyme or to your muscle fibers so that they twitch? And what they do is they attach an ATP to whatever it is. So if it's an enzyme, an ATP will attach to it. If it's a muscle fiber, ATP will attach to it. And then this bond will break. So here's ATP. And there's ADP, diphosphate. And then that goes away. And that energy, because it broke, is added to whatever is reacting. So it's an enzyme. The enzyme will literally change shape. If it's a muscle fiber, it will twitch. It'll pull its fibers in. And that's how you get energy. So it moves energy around your cells by moving this chemical. This is a chemical that everything knows how to use in your body. To the point that you have a lot of processes that are devoted to detecting AMP, adenosine monophosphate. Why would your body be extremely concerned if adenosine
Gives
monophosphate
it
is
no
hanging?
energy.
You have no energy left. So like a lot of emergent things would happen, kick in some adrenaline, start sucking the energy out of your glycogen in your liver, and do a bunch of other stuff. And all of it based on what, because you don't just burn sugar, you transform it into something your cell can actually use. Okay. Draw what you think this should look like for an endothermic reaction. I also should keep an eye on the time because I don't want to use up all of it. We need to get in the lab at some point. Poor people. Okay. And make sure you do it in pencils to erase it for when you get it incorrect.
Thanks.
And I'm not saying it is incorrect. I just realized when you wrote in pen, I wasn't commenting on the quality of your joke. I mean, if you're confident, pen is good. Or you're required to never, ever to show all your mistakes, pen is great. Any of you grew up in a system in which they awarded you a pen?
Yes.
What grade did they do the pen in? Hold it. Year 5 is grade 4? Is kindergarten year 1 in the UK? What country? Oh, okay. There. Good. Maybe shorten that just to make it a little bit more obvious, but good. Okay, I think everybody did get it. So it's probably good you drew. Oh, now I forgot where I put my pen. So we can go the other way. We have H2O. We have the activation energy. And why did it look all funny like that? It's like, oh, because it thought I was using 2. Now the activation energy includes both the change from the beginning to the end and the amount to get over the hump. So we've got the activation energy there. And we have our change here. This is our delta H. It went from here to here. So it is positive. So it is endothermic. So which has more energy, products or reactants?
Reactants.
In their bonds. Products. Because it's physically higher. We can measure it. The products have more energy in their bonds. This is why plants are so useful. We want to save the environment. Not because we like plants, but because we can use them.
I also like plants though.
Yeah. Because we can make them do stuff.
I also just like plants for plant's sake.
Oh, that's just silly. We want to do stuff. Get some genetic engineering in there.
No, thank you.
Make them
And now
glow.
that's photosynthesis.
Genetic engineering, we pulled the luciferase gene, called such because it glows, out of fireflies, and we put it in oak trees. And made oak trees that glowed at night.
And cats.
The oak trees, they had grown in a little test tube, they proved they could do it, and then they destroyed every single one of them.
Why?
Exactly. We could right now have forests about 50 years old of oak trees that at night would glow. It'd be like a fairy forest walking through. It'd be fantastic. They had some concerns about like, ooh, how will it change the environment and animals will change. Who cares?
They could just do that
Glowing
for one
forces.
forest.
Well,
No.
they were like,
No.
seeds will move around again.
No, that's true.
But who cares?
Well, except
Glowing forest animals will adapt. It's
oak
called
trees.
evolution.
Oak trees can barely like. There's so few acorns survive. Like,
Exactly. We
oak
should not
trees
worry about such small things.
So like takes so long to spread. Like if it was like a I don't know a hawthorn, then I'd be concerned. But an oak.
An oak, fine. If you're going this way, the mitochondria is the powerhouse of the cell. But what does this?
Photosynthesis.
Yeah, what organelle? What organelle goes this way?
Chloroplast.
Chloroplast. And they don't use ATP as their energy to do that. What do they use?
Sunlight.
Yeah. So then we can take something that's really low energy and put it into high energy bonds. And so in that case, they take something that's low energy and with sunlight get over there and make it high energy, and then they can store that. And they store it as starch. They also store it as cellulose. You can eat starch, like in a potato, but cellulose is what makes the hard part of trees, and you cannot digest it. It's what we call fiber. But it's all just made of sugar. It's still variations of sugar. Oh, right. Energy term.
Starch in their inner bark.
So based on this, where does the energy term go in the reactant? If this is an endothermic reaction, would we put the energy term here, or would we put it there? Is it coming out or going in? Yeah. So we could say, like, we want to put numbers to it. We could say like 100 kilojoules, or we could say energy, because we put that energy in. It went up. So this means you put energy in, the reaction goes. But as soon as you stop putting in energy, it just stops. Because you don't end up with more energy than you gave off. You end up with less energy, so there's not enough again. So as soon as you stop doing it, the reaction will stop. So it's not that it sucks in cold, although there are reactions like that. It's that it won't go unless you keep adding energy. So this is cooking pancakes. You have batter, you have cooked pancakes at the other end. If you stop cooking them, they don't magically become pancakes. It just stays as batter. Whereas a forest will burn itself. Once you light it, energy comes back, and then you get more energy that allows it to do it again and again and again, and it can just keep going and going and going because you're always getting more energy out.
Trees.
Pardon?
So you run out of trees.
Yeah. Success.
No.
Great success. So for this, where would the energy term go? Products or reactants? Products. I'm going to set up a reaction to show you. While I'm doing that, I'm going to have you start on a worksheet about energy in reactions. Yes, that is my name. Well done.
If they genetically engineer trees to grow, why do they, and they're concerned about the environment, why do they just remove its ability to reproduce? Make it seeds dead?
Have
Do
you
that all
have
the
you
time.
have you seen Jurassic Park?
But also trees aren't like that. Well, not oak trees aren't. Oak trees are already both genders.
Yeah, but but the question was, have you seen Jurassic Park? Yes. Life finds a way. And what is that? Is what he was implying when he said that was that there are so many ways for genes to get passed around. A virus can infect the tree and carry it to another plant, like hawthorns. All we need is a disease that infects both. So once it's in the environment, it won't stay in oak trees. It may stay there for a while, but there's a good chance that eventually something will carry it over. Right now, there's a few things that have never crossed over. Fungi are the only fungi. Hold it, no, and some bacteria. Two. Are the only things that can digest cellulose, which is why they're important for breaking down the forest floor, and like the interior gut of cows will use that to digest it. But mammals can't, and it's never crossed over. If, however, genetic engineering again.
What part of the tree glowed?
Oh, the outside, like the leaves.
The leaves, not
Yeah.
the wood.
Oh, the wood too.
Okay.
Yeah, everything.
Really?
It
That
was
would be
pretty.
so cool.
Yeah.
When they
We should, in one of our classes, just make it and like go plant it somewhere in Hobay, and just
If I had access,
you know the cost about it.
they invented a type of rice that it was a lot like golden rice, which they're also doing to boost vitamin E because it reduces in areas that are low in vitamin E. It was a way of introducing it. They made a particular variant that was more resistant to drought. They had a small group. It was done with genetic engineering, and they're like, this might actually really save people. And then a group came in and said, no genetic engineering. And they killed every last plant. And they actually lost the gene. It was really hard to get it in. They haven't been able to duplicate it since.
I like genetic engineering.
Well, as long as it's like food and not like killer mammals.
When we were testing the first genetically engineered hypoallergenic
Oh,
cats,
there we go.
they made them glow in the dark so they could visually see if the genes worked because they put them together.
Yeah. They'll do that with things like they'll make a group of mice. Okay, you have the worksheet. I'm going to start on a demo. I'd like to show you about endothermic reactions. So just start in the worksheet. It's intended, essentially, it has you draw a couple of diagrams, label them, and then answer the definitions to make sure that you're familiar with the material. They'll make like glow-in-the-dark veins and arteries, which can seem odd because you'll never see those, but it means when they dissect them, they can tell them apart.
They made chickens with dinosaur beaks.
Oh, that's a matter of turning the gene on.
Yeah, but still.
The genes for teeth are already in birds because they are dinosaurs. In fact, you know how you have to eat fruits and vegetables for your vitamin C? You actually have the gene to make vitamin C. We are, I think, the only ape species that can't make its own vitamin C. You make it in your liver, or you're supposed to. But at some point, roughly 250,000 years ago, a species of ape lost the ability to do so, and we are descended from that species. It might have actually forced us to evolve in a different way because we were more concerned about moving and ensuring we had access to fresh fruit, because any group that didn't died out because they didn't get enough vitamin C.
250,000 years, we were still
Maybe
Homo
longer.
sapiens.
Well, we lost it at some point.
But we were already across the world that long ago.
Oh, maybe it's 2.5 million. It's a zero here. One of the two.
100,000 years ago, a star cluster lost a star,
Yeah.
and we still have myths that talk about a star cluster with 7 stars and one disappearing 100,000 years later, and from all over the world.
That's
so
pretty
we
cool.
saw it, and we're like, that's weird. Let's tell that forever, and we never
So
forgot.
I am going to arbitrarily say then, I put an extra zero on it, say it's not 250, it's 2.5 million. At some point. What was it? 32. But,
saying ecological environment again.
Which one? What?
Ecological environment, because there are other environments.
We should make a glowing tree and release
Oh,
it.
wait,
No,
who's
which one? Yeah.
Why?
blowing.
Then we could have glowing trees
And we
you
can
know,
disturb
stand
everything. Our grandchildren don't need glowing trees.
They would love it.
They need normal trees.
But the glowing trees can see things, don't they?
They also can destroy ecosystems.
Yeah. We need glowing trees. Could you imagine how cool it would look from space to see all the forest is lit up?
That would create light pollution and no one could see the stars.
It would be fun when we have glowing trees.
You're short-sighted and immature. You don't even know that it's open on the phone, do you?
I've never heard of a hot spring. I'm sorry, I'm not in
Okay, now we're gonna see the snorkel words for real.
Oh, yeah, let's test it.
You know, I spent like 2 hours having the guy working with the guy setting up the super lab, and he kept telling me to set up the snorkels in different ways to see the best way they look. And then no science teacher put them back after the first 15 minutes they were allowed in.
Good, yeah. And every time I come in, they're in a different position. Okay, come on up. Move these desks a little bit, stand up, come on over, you have to look. Come,
What am I
come,
looking to?
come, no, you're gonna look and touch. When I tell you to touch, and only the spot I tell you to touch. Come, because that's important. Come, come. If you can stand, more people will be able to get around you. Okay, up on a wooden block to make it a little easier to see. Now this is a bit of an unusual reaction in that we don't often have two solids reacting. So that in itself is worthy of note, but it's also a bit of a cheat. Barium hydroxide, which is one of the reactants here, is barium hydroxide octohydrate. And so as an octohydrate, it has water in it, and so that's going to slowly get released. It's a good test because the actual reaction gives off a fair amount of ammonia. I would normally just do it in the classroom without a snorkel, but it is a little sneaky. Yeah, I've got a fair amount of air going. So what can you tell me about the reaction? We got a fair amount of liquid in there, and change of temperature presumably. I can now lift it up, and this block froze on. You feel underneath. It is going to be stinky to bring it out. This is the equivalent of opposite of a fire, in that you have a reaction going spontaneously. I don't have to keep adding energy to it. It is sucking the energy out of the room until it's done, just like the way the fire gives off energy into a room. There we go. And so this reaction is a little different than the other endotrope. You don't have to keep cooking it. It will just go on its own, because there's a second fundamental force we don't tell you about until grade 12, and that's chaos. So we have everything wants to be low energy, and everything wants to be chaotic. And this particular reaction gives off a gas, that's the ammonia I'm trying to get rid of, and it gives off a lot of water, both of which are far more chaotic than a solid. And so going from a solid to a liquid and a gas just pulls that reaction along, whether it wants to or not, and it just, because it requires energy, it sucks it in from the environment around it to the point that it will freeze water. Cold packs that you get are a little like this. They're often, they're not this particularly, you don't want something that's giving off ammonia, so it's not this reaction, but it's something like that, where you break it, it adds water, and then the reaction that happens gets really cold, and you can put that on yourself as a temporary cold. So, one of the very few endothermic reactions that'll happen spontaneously without heating it. Thank you. I'm gonna go put this in the
Isn't like cold a low energy thing?
Yeah.
So, but it right now it's colder, so it has less energy.
It has less energy, so the reaction is going to go slower and slower over time. But it's going to keep driving it because in that particular reaction, we have barium hydroxide.
Does it have more energy?
Plus, what is it? Sodium thiocyanate? No, ammonium thiocyanate.
Of the papers.
Goes to barium thiocyanate.
Also, I just intentionally.
I forgot about that.
Kind of unbalanced, I think. Okay, so we're missing its H in there. But roughly speaking, that's the reaction. So this reaction goes like this. So this is taking in energy. I don't know what it is. Let's say 100 kilojoules. And so as it's taking in that energy, it's getting colder and colder and colder and colder. The reason it's going spontaneously is there's an entire second force in the universe. And that is, this is a solid, and this is a solid, but this is a liquid, and that's a gas. And gases are much more random and chaotic than solids. And liquids are more random and chaotic than solids, and everything tends towards chaos.
But isn't cold like this ice? Isn't that a lower energy than it already started before? Like before it was a solid that wasn't cold.
Right?
Yeah, so it should be like the other way.
No. Did energy come out? Like when we did the gummy bear.
But anything that's cold is low energy, lower energy.
No. Anything that's cold possesses less energy. It isn't low energy.
Oh.
You could have a molecule that's very low energy. You've heated it up. The molecule hasn't changed its bonds. The amount of energy something has is based on its bonds, not based on its temperature. Temperature is just how much you've given it.
Oh, okay. So energy changes on how many bonds it has.
How many and what type?
Yeah. Okay,
Yeah.
like they're like the high energy bonds or not.
Yeah.
Yeah.
And so it's an endothermic reaction. The reason it's cold is because it's taking away energy, so the environment's getting cold. And it's most reactions, even if it gets more chaotic, aren't quite enough to overcome the amount of energy it takes, so they won't spontaneously keep going. But that reaction will, because it's so chaotic at the end. Yes?
Use the washroom.
Yes. Now, what do we got for time? And now it's time. You can get out your lab books. And does anybody need another lab sheet? Excellent. Take out your lab books. Get on lab goggles. Meet me over there, out in the lab. And I will stop the live stream because we don't need it.